Just a quick reminder of where we are. It's Tuesday, and in 2 days on Thursday is when assignment 1 is due, and assignment 2 will be given out. So we're learning today the last bit of stuff that you'll need to know for assignment 2, which is being given out on Thursday. And you have all received that email with the assignment links. Just remember that all the links were given to you in that one email. You're not going to be receiving an email for every assignment. So make sure that you save that email with all the links somewhere, just in case it gets deleted from your email or whatever, you want to have those links. And assignment 2 link will become active whenever I upload those assignments. I sent out a little poll last night on Discord to just get a quick reaction for whether or not people wanted to actually implement this memory pool that we're going to be learning about later in the course. And it's around tied, and there are fewer responses than the number of people in this room. So if you didn't see that, just go give a little thumbs up. I'm interested in how people think about that, because I think it's actually one of the more interesting things in the course. So we'll see if we end up implementing that or not. All right, so today we're going to be talking about this EntityManager class that we'll be using throughout the course, and a little bit of math for games. Okay, I just pressed the slideshow button and we're spinning. There we go. So, data management. I cannot stress enough how important this one sentence is. If you take nothing else from this whole lecture, take the first sentence. And that, in my opinion, one of the most important concepts in all of programming is separating the logic of what you're trying to do from how you store the data to do that thing. One of the most important reasons for this is because of just mental separation. Okay, so I don't want to necessarily have to keep all the details of how data is stored in my head when I'm also trying to write the algorithm to do the logic that I want to do. I want to be able to say things like, hey, give me a new thing, store a new thing. I don't want to have to worry about indices or pushback or any of this kind of stuff. I just want to be able to work with data while I'm trying to do more conceptual logic. So what we're going to do is create data structures which manage the data for us so the logic code doesn't need to worry about it at all if possible. And so your complex algorithm should, like I said, just say, give me some data, or take this data, or store this, or log this. It should never need to know all of those implementation details. So whether or not it's a set, or a vector, or a map, or whatever, or a dictionary underneath the hood, it shouldn't need to know, you shouldn't need to parse all of those details while you're trying to write this complex physics equation or something like that. And so what we're going to do today is make something called an entity manager. That's what we're going to do. And we're going to make this in this course. And what's going to happen is for assignment 2, I'll give you the skeleton code of the entity manager. And you just have to fill out a few of the functions in the entity manager. So you do it once. And then for assignment 3 and assignment 4, I'm just going to give you the completed entity manager in the way that I did it. So you just have to do it once. You don't need to recreate this thing every assignment. But I do want you to get those details and implement those details at least once on your own. So the entity manager uses something called a factory design pattern. In software engineering, there's this design pattern called a factory. And we're not using all of the features that the true factory design pattern uses, but you can just picture this as a class that handles the creation and management of a particular type of thing. So the entity manager will handle all the creation, storage, and lifetime of all of our entity objects. Because if you think about it, in a video game, we're creating lots of stuff. We're deleting lots of stuff. We're storing lots of stuff. And so ideally, what we would want to have is one place where all of that is taken care of for us and make it as easy as possible to use while we're doing it. So some of the functions that the entity manager may have are things like addEntity. So we want to create a new entity to spawn a bullet or an enemy or something. Also remove entity. So maybe, two things have collided. We want to be able to delete those somehow. Maybe we want to, store all of our entities there or do some bookkeeping. So for example, maybe I want to know for performance benchmarking how many entities currently exist in my game, right? If I was just creating entities all over the place, I would have no idea maybe how many entities exist in my game, or how many am I creating per second, or how much memory are my entities taking up. All these things are things I would want to be able to profile or benchmark. And if we do use this factory pattern, and that's the only place that entities can be created, then it's trivial for that factory to keep track of all those details. So it's another added benefit. So the factory should also somehow ensure that the user cannot create its own entities. So only the factory can create entities, and we'll show how that does that a little bit later. And last time we talked about these things called entity tags. And so we may want to group entities by functionality. And so each of our entities is tagged by a string. So for example, a tag may be just a very simple type of entity. Like down here we have a tile entity. Maybe we have a background entity. Maybe we have a player entity or a bullet entity. And usually what we do is we tag things so that we're grouping by behavior, right? So all the tiles here are pretty much going to act the same way. All the bullets are pretty much going to act the same way. If you have an enemy bullet that acts differently from the player bullet, maybe you should tag it enemy bullet or player bullet or something. And what's going to happen is that the entity manager, yes, it's going to store all the entities, and if we want to get a vector of all the entities, it's going to say, here's all the entities. But something we may also want to be able to do is quickly get all the entities of a given tag, right? So give me all the bullets. So yes, I could get all the bullets by iterating over everything and then saying, if it's a bullet, do this thing. But wouldn't it be nice if I could just say for each bullet, right? And the entity manager is going to be able to do this for us. Yeah, so example, maybe loop over all the bullets. So here really quickly, before we get too much into the entity manager, just a quick recall of how we designed our entity class last time. It has this component tuple, which is a standard tuple of all the different components that we have in our game engine. Then we have a bool, alive, and if it's false, then this is going to be deleted by the entity manager. Here is our tag. This could be bullet, player, etc. And then a unique integer ID associated with every entity. And then we have, helper functions for all of those things. So the entity manager will trade some memory for additional functionality, right? We don't get anything for free in computer science. We always have a little bit of a trade-off. And so the two ways that we'll store entities are, first, we're going to store all of our entity objects in a vector. Okay, so we'll have all our entities, they'll just be in a single contiguous vector. And then we will also store separate vectors of entity objects by their tag for quick retrieval. So if we have a vector of entities here, what we're going to do is we're going to use a little bit more memory, and we're going to have this map from strings to vectors of entities. So for example, all of our bullets, all our players, all our tiles are going to be in the big vector of everything. But we're also going to store in this map, say, for example, a bullet entry, and then have a vector of all the bullets, right? Or a tile entry and have a vector of all the tiles. And that way, I can use double the number of pointers to save on computation in our engine. So this is one of those things that, on a particular piece of hardware, or with, an entity of a given property, this may not actually be faster. Maybe it actually is faster to store just a single vector of all the entities and then iterate through it and eliminate the ones that you don't want. But in practice, it's a bit faster. And not only that, but it's a bit more convenient to use and makes your code a little bit easier to write. And so that's what we're going to do for this class. So when we talk about an entity manager, I just said that we're going to store our entities in vectors, but how are we going to store those entities in the vectors? There are a number of different decisions that we could make here. The first one, and the most maybe easy and intuitive and obvious one, is just store entity objects directly in this vector inside the entity manager. So we have this entity vec, which we're going to say is a standard vector of entity. Okay, so that would just be a standard vector of entities, simplest possible thing we could do. The second thing we could do is we could say, okay, let's store smart pointers in the vector. So we're going to use these shared pointers, which are a type of smart pointer, and store those in the vector instead of storing the whole entity itself contiguously in the vector. The third way of doing it would be to use a memory pool to store entity data, in which the data for our entities is not stored in this vector at all, and we'll get into this a bit later in the course. It turns out that this is going to be what we would actually want to do if we had the time and the inclination to do so. So which of these two are we going to do? Well, let's have a look at that. What happens if we use a standard vector of entity? I'm going to have some pluses and some minuses for each of these things and then tell you which we're going to choose for this course. So first of all, it avoids the overhead of smart pointers. Smart pointers, unfortunately, have a little bit of overhead. They're called reference counted smart pointers. There's a little bit of overhead with that reference counting. In terms of our game engine, they would be just fine, but this would be a little bit faster in practice. The entity data is stored contiguously in memory, which is really nice, helps the cache. It simplifies the overall design because this is as simple as you could possibly get for storing a collection of things, right? Just a vector of the collection of those things. However, some of the negatives are the ownership, the references, and the lifetime of the entity object are tied to the container directly. And one thing we're going to talk about a little bit, which is iterator invalidation today, is that if the entities are stored directly in the vector and the vector gets resized, it's possible that any references we have to entities living in the vector are now completely invalidated, which would be like your program would just crash or have unintended behavior if that was the case. Removing an entity from this vector can be really slow. Why? Let's say each of our entities stores like, I don't know, a kilobyte of data. And you have 1,000 entities in this vector. And now you want to delete the third one, right? So the way you should all know by now in fourth year that a vector would delete something is by taking that something, taking it out, and then shifting everything else over to the left. So in that case, you would be shifting 96 of these 1 kilobyte objects all the way to the left. Yes, there are other ways that you could possibly delete from a vector by swapping and all this kind of stuff, but taking and moving all of that data around is slower than just moving a pointer, right? So it can be a little bit slower. And reallocation of the owning vector can invalidate existing references to the entity. Now, we could deal with that, but then our code gets a little more complex, etc. Let's compare that to using a shared pointer to entities inside this vector. Well, the good thing is that shared pointers have shared ownership, meaning that we can safely refer to those entities at any time in multiple systems, and we know that it'll be safe, right? Automatic memory management. We don't need to worry about the lifetime of this vector because the shared pointer will just handle everything using RAII. Adding and deleting from the vector itself, because the shared pointer is less data than the entity itself, that'll be far less data to shift around. And so the actual adding of things to the vector and the deletion of things from the vector will be a little bit faster. However, the creation of shared pointers of entities is slower than the creation of entities themselves. And we can modify the vector while still referring to entities in other parts of the code. That's good. Those references won't be invalidated because we're not using references. We would be copying it. However, the negatives are the smart pointer overhead is obviously slower. You know, if you have a wrapper around something, that by definition is going to be slower than just the something itself. Our entities are no longer stored contiguously in memory because each of these shared pointers is going to live on the heap somewhere, right? So using the heap is a bit slow, not great. It's a slightly more complex design overall. Why is it more complex? Because we just have this wrapper around our entities rather than using entities. And I always get a comment from someone saying, why not use unique pointer? Because unique pointers don't have these reference counts and they don't have the same overhead. However, they still use the stack, or they still use the heap. And there's two things we want to do with the EntityManager class that I have not been able to figure out how to do, by using unique pointers, and shared pointers just work. And it turns out that because the memory pool solution is the one we want to use in our AAA game engine anyway, it's not really worth it to hammer down and try and optimize the hell out of something that isn't the optimal way to do it anyway. So we're going to look at these things and we're going to say, okay, the first one where we store entity objects directly, I kind of want to avoid the problems that can cause. So that has some memory issues we want to avoid with stale references and stuff. So I don't want to use that one. Smart pointers are more robust. They're safer, but they're slightly slower. And so that's the trade-off we're going to use, and we're going to use this for now. So assignment 2, at least, is going to use this way. And it turns out that the memory pooling stuff, that is what you would want to do eventually, because what it does is it's going to store all of this data in a huge array in memory somewhere, and the entity then just becomes an integer index into that array. So you can pass entities by value everywhere you want because they're essentially just an integer. They're so small. And so that is what we should want to do eventually, and that's sort of what that poll was last night. Do you want to just keep it, like, use this the whole course, or do something pretty neat, implement a memory pool, and use it the probably correct way? So what we're going to do is we're going to use number 2 because it just offers a nice balance of everything at this point in the class. So the Entity Manager, we're going to use some type defs here. I know I've been using, like this should actually be using entity map equals this, or entity vec equals this thing. And that's what will be in our code, but it just didn't fit on the slide in a nice way. So type def just means, instead of typing out this whole big thing right here, I'm just going to say entity vec. So our entity vec is actually going to be a standard vector of standard shared pointers to entities. And then this thing which I'm calling an entity map is a map from strings to vectors of entities. So for example, this map here could store, a tag of tile to a vector of all the tiles, right? So that's the way we're going to do it. So what are we going to store in the Entity Manager? We are going to store our entity vec of all the entities, right? So this is where all of the shared pointers to all our entities is going to live in this first one. Then we were going to have a second copy of all of those pointers in this map. And so this is that map we talked about. And then we're also going to do a little bit of bookkeeping where I'm going to have the total number of entities that I have ever created, right? So if I want to get the total number of entities that exist right now, I can just say mentities.size, because I'm currently storing all my entities in it, so I can get the current number of entities. But if I want to know, for example, what's the number of entities that have ever existed, then I can store that here as well. Also, the Entity Manager is going to be creating new entities all the time, and the entities are going to have a unique integer ID associated with them. And so in order to guarantee that each newly created entity has a unique ID, what we can do is just, whenever I create an entity, I give it this ID, and then I increment that number, right? And then I create another entity, give it that ID, which is now 1, and then I increment that number. And so I'm guaranteed that as long as I don't create 64 bits worth of entities, which, good luck having that much RAM or that much time in the universe, I should be okay for using this. And then the functions we have, well, we're going to have a constructor for our Entity Manager. We're also going to have a function which allows us to add an entity, okay? And I'll show how that addEntity functions in a second. Then we're going to have a function which gets us the vector of all the entities. That's just getEntities. And then I'm going to have a function which, if I pass in a tag, it's going to give me the vector of all the entities of that tag. And so this is the basic functionality of the Entity Manager. It's going to be able to add entities and get entities and bookkeep all the stuff related to entities. So let's first look at that addEntity function. And what it's going to do is it's going to create a new entity object in here. Then it's going to store that in the vector of all the entities. Then it's also going to store it inside the map for its tag. and then it's going to return the shared pointer that points to that entity. Now you may say, well, why do I want to return a like the shared pointer to the thing that I just created? We'll see that in a second, why you're going to want that functionality. And so how this is going to work in practice, now this is not the exact code you're going to use for the assignment, but just to show some sample C++ code. In order to make a shared pointer, the way that we want to do that is there's two ways you can do it. You can say like standard shared pointer and then put in a new pointer. That's sort of the old way of doing it. But there's this standard make shared, and standard make shared is templated on the type. So that's how we create a standard shared pointer to an entity. And then in here, these are the constructor arguments for the entity class. So we would take in the tag, and then also what this does with post increment is it passes in the total number of entities. And so if this was 0, it's going to pass in 0, and we'll use that for the ID of the entity. And then with post increment, after that line, that whole line has been completed, then it's going to increment that number. So rather than saying pass it in and then on the next line increment that, we can just do that all in one line. I'm sure you know how to do that. Now what we have is we have this, so auto here, this is going to know this is a shared pointer, right? So this is a shared pointer to an entity. So what we're going to do is we're going to add that shared pointer to the vector of all the entities. We're also going to look up in the map the tag, and then that map indexed by the tag is a vector of all the entities of that tag. So we add it there as well. So we store each shared pointer twice, and then we return that shared pointer. That's it. It's pretty simple to do something like that. So how would you then use this in practice in your code? Well, let's say somewhere in my class, in my game class, I've got this private member variable. We're going to call it m_entities. This is exactly how we're going to do it in assignment 2. And then somewhere, I'm going to want to create a new enemy, for example, right? So the spawn enemy function is going to say auto e equals mEntities.addEntity, and then give it a tag. And the reason we want to have that reference, or the copy of the shared pointer, is then I can just add all my components to it. So, hey, EntityManager, please create me a new entity. It's just going to default construct this entity and give it the tag and the ID. And then now that I have that, I can add my transform component, I can add my shape component, I can add my bounding box component, I can work with that as much as I want. Okay? So that's how we're going to use it, and it's going to be just that simple. And we don't need to worry at any time about the creation of entities, like how does that work? How does the Entity Manager take care of all that stuff? How am I going to remove these or destroy these? Is it stored in a vector? Is it stored in a map? None of that matters because it just takes care of it for us. Right? So that's really nice. This is as simple as it could possibly be, is just, hey, give me this new thing that I want. Who has heard the term iterator invalidation before? Oh, wow. So this is going to be a great lecture for you, because this is going to be not a big part of your life, but it will happen to you at some point, okay? Iterator invalidation is a very important concept, and it's caused by modifying the contents of some sort of collection while you are iterating through it, okay? So we'll see an example of that. It happens all the time in games. For example, adding. While we're iterating through entities to check for explosions or for collisions, let's say, so I want to iterate over all my bullets and then iterate over all the enemies. So I'm inside a loop. Now what I'm going to want to do is, well, I'm currently inside a loop iterating over all the entities. I've detected a collision, and now I want to spawn another entity, which is an explosion, right? And so I'm modifying the collection that I'm currently iterating over, and that can have issues. It can also happen with removing entities. So let's say I'm iterating again over, all of my bullets and enemies to check for collisions, and within that, something has to die. And so what I'm going to do is I'm going to remove the thing that dies. Maybe it's the bullet that gets deleted or whatever, but I'm removing something from the iterator as I'm going through it. And that can cause iterator invalidation. And iterator invalidation, the result of that can be as good as your program crashing. Believe it or not, that's the best possible scenario. But the worst scenario is it does something that it doesn't crash, and your results are just wrong. Like, it could skip over something inside your iteration, right? Or what can happen with adding is that if you add something to a vector, but the vector is full, the internals of that vector, will actually resize the vector, creating a new array in memory, and now all of those things that you've done with that vector, all of those iterators are now invalid and could crash or could have unexpected results. There was a question?
Yeah, is it the same thing as in like in Windows operating system? Like, I don't know about Mac and others. Like when you open a file, you cannot like rename it at the same time. Is it because of like iterator invalidation?
So the question was, is it like if you have it open, can you modify that file somehow?
Kind of like rename it.
So no, that's something completely different. This is more of, I'm iterating over a collection in my code, and now the iterator itself that I'm using to go through this thing can be invalid. What you're talking about is just, hey, a file is in use, so the operating system doesn't let you delete it. Yeah, that's a separate topic, but it's also important. So vector functions can cause reallocation, right? So I kind of just talked about this. If I add to a vector via pushback or insert or whatever, the vector may have to resize itself. And what it happens is it creates a new array, copies everything to the new array with the bigger size, and then deletes the old array. And so any iterator that I've been using to iterate over that, meaning like if I use like a range-based for loop or something like that, right? If I say for auto e in vector, and then I add something to the vector, the iterator could just completely, I don't know. I don't know what happens, but it could be invalidated. Erasing elements may invalidate too via a different mechanism. So if we remove from a vector, it could also invalidate all of those iterators and references, or if you have written your loop poorly, it could also skip over things and you could miss things that you're trying to do. So here's an example in code. Let's say I've got this vector of bullets and I've got a vector of tiles. Right? So I wouldn't have these vectors in our game engine. The EntityManager would handle all of that, but I just want to, this is for an example. So I'm going to iterate over all of my bullets. I'm going to iterate over all of my tiles. And then if there's a collision between a bullet and a tile, I want to erase the bullet. Right? This seems simple enough. But the problem is, I'm currently iterating over all of my bullets. So if I modify a vector, or any collection, while I'm iterating over it, it could have disastrous results. And we don't want to leave that up to C++ because it's undefined behavior in some cases. So all the iterators and values of B after the erase may actually be invalid. This may not be intuitive why this is right now, but trust me, it happens and it sucks when it does happen. Especially if it doesn't crash, because it just, why did it happen 2 different ways when I ran my program 2 different times? Well, it's because of this. So what we're going to do is we're going to introduce this concept that's going to avoid iterator invalidation completely. And what I'm calling this, I don't know if other people call it this, but I'm calling it delayed effects. So we're going to delay the effects of the adding and the deleting in our entity manager so that we guarantee we're only doing it when it's safe to do that. Okay? So with the entity manager handling the entity creation and destruction, this becomes really easy. Because since we're only ever creating or removing things via the entity manager, all those details are going to be completely hidden from you. And you can iterate over everything that you want, you can add things whenever you want, you can remove things whenever you want, and the only person who ever needs to worry about iterator invalidation is the person coding the entity manager. And so just imagine if you had to deal with all of that while you were trying to write collision code and stuff. It would be a nightmare. So the idea here is to only add or remove entities when it is safe to do so. And when do we know that it's safe to do so? When we're not doing anything else, right? So let's just put it at the beginning of a frame. So the result that this is going to happen, the result this is going to have is that if I say add an entity, it's not actually going to appear on that frame of the game. It's actually going to exist on the next frame of the game. And if I say remove an entity, it's not going to be immediately deleted. It's going to be deleted at the end of the next frame. Okay? And as far as I've been, if you have any issues with this, I don't think you will. I've never had issues with it. But just keep that in mind, that like if you add a bullet on this frame, it's not actually there. It cannot actually collide with anything until the next frame. So everything is pretty much one frame delayed in that way. So the way we're going to do this is we need to modify the entity manager just slightly. So this is what we had before, and I've put in a blank line here just to show you what's changing. And the only thing that's changing is we're putting this in this additional entity vector of things to add on the next frame. So what we're going to do is when we add an entity, instead of immediately adding it to those vectors, we're going to instead put it to that queue of things that we want to eventually add. And then we have another function called update. And what this is going to do, we're going to call the entity manager's update function at the beginning of each frame. And then that update function is going to take the things that we wanted to add and actually literally add them to those vectors. Why are we doing it then? Because we know this is before any of the physics. We're not in any other game loops. Nothing is going to be accessing these vectors while we're doing this. Okay, so let's have a look. So this is the addEntity function that we just made, but now we know that we can't do it that way. We're not immediately adding things to the vector. So what we're instead going to do is we're going to give the vector the increasing entity ID, or sorry, the entity. It's the same way of creating the entity, but instead of immediately adding it to the vectors, we're going to add it to this toAdd vector queue, or entity queue. And then we're going to return it as well. So I can say add, and then immediately use it to add the transforms, do all the things I want to set up this entity, but it's not actually going to be usable from the entity manager until the next frame. Then, this update function, which is called at the beginning of each frame by the game engine, it's going to do the actual adding for us, right? So what this is going to do is it's going to loop through each of those entities that we want to add and then push those into the vectors that we actually want them to live in. And then at the end of that, because we don't want to be adding these same things every frame, we have to clear that, right? So we take everything we wanted to add, we actually put them into the vectors, and then we clear the things that we just added. Okay? So hopefully it'll make a bit of sense, but instead of adding directly, we're just delaying the effect of the add until the beginning of the next frame. Similarly, we can do this with entity death and removal as well. So with this system, we can easily do that. And so each of our entities has this alive bool variable, and all we need to do is set that to false when we want something to die. I say die, but just be removed. So the entity manager update will read that variable and remove the entity if it's false. Couldn't be simpler. And what this does is it prevents the removal iterator invalidation. So the previous thing prevented the add invalidation. This one will prevent the remove invalidation. So here's our update function. This is what we just wrote, which is the adding part where we go through all the things we want to add and remove them. And then I'm putting this in pseudocode here because this is part of what you have to do on the assignment. And that is go through all of the entities, and if E is no longer alive, remove it from all the entities, as well as removing it from the map vector as well. And then you clear madd. And if you've been paying attention, you may say, but Dave, didn't you just say we were trying to avoid iterator invalidation? And what are you doing here? You're iterating through entities and removing stuff from entities. So this is going to have iterator invalidation. So it's like iterator invalidation all the way down, right? Now, it's possible to do that, right? It is possible to avoid iterator invalidation when you are removing things. It's just, you've got to look up that syntax in C++, okay? How you would actually do that. And then once it's done here, it'll be good forever, okay? There's also a function in C++ that can do this for you. It's like standard remove if. So you can, the syntax is a little bit tricky, but it's like standard remove if. And what it will do is iterate over a collection, check for a lambda function, return. And so that lambda function could be, is this alive? And so you just say, okay, remove everything from this vector if its alive variable is false. And it'll just do that removal for you. So that's one way that you could possibly do this. But that's it. Once we have this done, our whole program, it doesn't matter where we're iterating, we can add things, we can create more entities, we can delete entities, etc. Just keep in mind that the only one little annoying thing here is that things are not truly deleted until the next frame. So, for example, if I'm iterating through, the bullets and enemies and I've destroyed an enemy, I'm going to set its alive to false, but it's not removed from the vector. So if I go iterate later in the same frame and iterate through enemies again, that enemy is still there. It's still in the vector. But you can check to see if alive is false or not, right? So it's up to you. That is a game mechanic decision. For example, do you want an enemy to be able to collide with two different things on the same frame? If so, then you don't need to worry about that. If you only want it to collide once and then be removed, you might have to check to see if it's alive. So that's the only real annoyance there. It probably won't come up in any of our assignments. So how would you use this with the Entity Manager? Well, this is sort of like before. Let's say we're doing some collision checking. So mentities.getEntities bullet. So I'm iterating over all of my bullets here. Then I'm iterating over all of my enemies. And we're going to have this physics system. It's going to check if there's a collision between two entities. Here it happens to be the bullet and the enemy. And if there is a collision between them, and our game mechanics dictate that if a bullet collides with an enemy, they should both be destroyed, then we can just call, hey, destroy the bullet and destroy the enemy. And it couldn't be simpler, right? So what this does internally in the entity is just set the alive variable to false. And then at the beginning of the next frame, the Entity Manager will look over all of our entities and say, hey, delete all the things that are false. So we don't need to worry about storage. We don't need to worry about iterator invalidation. We just need to worry about our code, which is going to look super clean now that we've got this factory handling everything for us. Excuse me. So again, here is our entity implementation. The alive variable lets us do that destroy, which is monitored by the Entity Manager. The tag is going to let us get groups of entities by their tag or to check what the type of something is. And the ID is going to allow us to tell whether or not something is a unique thing. The only remaining thing to do is to add that update function to our game's main loop, right? So our main loop is the thing that's going to be doing all the top level logic. And so what we do here is before we call our user input, our movement, our collisions, rendering, before we do any of that stuff, just make sure that our Entity Manager is up to date. So the very first thing we do every frame of the game is call Entity Manager update so that we know, okay, all the entities that I wanted to add, they are added. All the things I wanted to destroy, they are no longer there. And then I can go ahead with my game logic. So, the last thing, I keep saying there's the last thing, one more thing that we have to do here is that, sure, we've got all this. This is great. Let me go back real quick. Where is this? Wow, okay, I went back pretty far. Yeah, here we go. So right here, where we were creating an entity in our game engine, we say, hey, Entity Manager, give us a new entity. Perfect. But what's to stop someone in our project, one of the group members who didn't come to class, from just creating an entity on their own, right? They could just call the constructor of the entity and create a new entity that is not managed by the entity manager. So how do we stop that? Well, if you read the title of that slide, it's probably obvious. We can ensure the safe creation of entity objects, meaning that only the entity manager is allowed to create them, by only allowing them to be created by the entity manager class. How do we do that? We're going to make the entity constructor private, so that and then we're going to add the entity manager as a friend class to the entity. And what this means is that friend classes, what's the C++ thing? Friends can touch your privates, but your children can't, or something like that, you know, like, so private methods, if you want another class to be able to call a private method, then you declare it as a friend, right? Not necessarily great life advice, but it works in C++. So the entity is going to have a private constructor, meaning that if I try and construct an entity outside of the entity manager class, it's going to be a compiler error. It won't let me create that program because I've said, hey, private constructor. Only the entity or friends of the entity class can create them. This way, we absolutely cannot create entity objects outside of the entity manager. The only small caveat here is that having a private constructor means that there's a slight hiccup in creating shared pointers to something with a private constructor, okay? So here, if we try and do this standard make shared entity, make shared is this other function outside of the entity manager class that is now trying to create an entity, and it can't. And since it's not a class, we can't declare friendship, and there's no easy way to let this happen in C++. So there's a slightly different syntax we can use for private constructor classes that we want to have shared pointers. And instead of using this preferred make shared function, we can just use the old school way of declaring a new standard shared pointer to an entity, and then inside its constructor, we use new to create an entity and then pass it on to the heap. Why? Because this can actually create them. So this is the way that we will create a shared pointer only in the case of entity, which has a private constructor. So that's just a small caveat that we have to make there. And that's not the preferred way of creating shared pointer objects, but we're just making that one exception for our design. So let's have a look at our game engine code now. Manually creating entities is no longer possible. So this is outside of the entity manager. This is in our game code. If we try to create an entity by ourselves with make shared, it won't work, compiler error. If we try and make a new entity on the heap using the new keyword, it won't work, compiler error. If we even just try and make a default stack constructed entity, won't work. We cannot do that. We have to use the entity manager. It's the only way to create an entity object now. And so that is sort of the factory design pattern, or at least what I'm calling the factory design pattern here. Yep.
So the code you showed us on the last slide where you were showing us to use the old school shared
Yep.
that lives within the entity manager.
Yep.
Okay.
Yep. And the reason it's able to create an entity via new is because it's inside entity manager, which is a friend of entity. Yep. Okay, so for that's the entity manager class. I'm going to give you the skeleton code of that class for assignment 2, and you're just going to fill in some details. You're going to implement that once, and then for every future assignment, I'm just going to give you a completed entity manager class because it's easier than having you retype it in every single time. Is 2050 still a prerequisite to this course? Math 2050? Who has not done Math 2050? Okay, so someone got a waiver, but that's fine. So all of you know exactly what I'm about to say for the next 20 minutes or so. Or what is more accurate is that you all knew what I'm about to say until the exam, and then you forgot it all, right? I did math as well. So these are just reference slides for assignments that you can use where I go over some basic trigonometry, vector stuff that you're going to need for these assignments. but it's also nice to have it used within the context of games, right? So if we're talking about the length of a hypotenuse, sure, that's all well and good, but it's also nice to know that that's actually the speed of the bullet or something like that, right? So we're gonna just look it over. So as a quick refresher, every game's graphics are drawn to some screen, you know, as long as you're not using some sort of 3D display, which none of us can afford. Screens are a plane, they are in 2 dimensions. Screens are made of small discrete elements called pixels. Pixels are, in modern times at least, square. And pixels have R, G, and B elements, and when R, G, and B elements are combined, they trick your eyes into thinking that it's a different color, right? So who's ever looked at a computer screen up close and you can see the individual LCD elements? Well, this is what it looks like when you zoom in, right? When you're super macro focused, you can see all the individual elements and it doesn't look like anything, it just looks like blobs. But then when you zoom out, hey, it tricks our eyes into thinking it's actually color. So in modern games, we're going to specify the color of an object in a specific color space. And the color spaces that, you know, that exist in a lot of software are RGB, that is red, green, blue. RGBA, which is red, green, blue, alpha. Alpha is a sort of transparency channel, if you will. So if the alpha part is 0, then you cannot see your object at all. If it's 1, then it is completely opaque. And if it's 0.5, it's sort of half transparent. So that's what the A is. CMYK, that's cyan, magenta, yellow, and black. That's used in printing. If you've ever been to a printer, they probably specify their colors there. There's grayscale, which is just, you know, one gray value between 0 and 1 or 0 and 255. There's monochrome, where it's like it's either on or off. So RGBA is the most common modern color space, at least in graphics libraries. And so this is red, green, blue, and alpha. And every pixel gets assigned an RGBA color. So that's what we're going to be using in SFML. So that's just a quick note about colors and how they work. 2D positions. If my face gets in the way on the video, I'll try and hide this. But our system display is going to be a pixel grid. And so this grid is given in 2 dimensions, X and Y. So I'm going to use a Euclidean XY plane to visualize individual positions. So each integer position is a display pixel. So over here, we're just going to be working with integers for now, and you can picture that as pixels on the screen. And just note that displays, you know, they can be resized or full screen. So if you have an SFML application and you've given it a specific resolution, which you then resize the window or make it full screen, you can have full screen applications that are running at a lower resolution than your monitor's native resolution. In that case, you would have sort of stretched pixels, right? They're not actually stretched pixels. The monitor does all that for you. But things, you know, 1 pixel that you have drawn to the screen may look larger than 1 pixel in that case. Just be aware that that can happen. And also be aware that most APIs, including SFML, have 0, 0 at the top left of the display. But just for these examples, I'm going to be using 0, 0 in the bottom left because the Euclidean plane is what we're most used to. But just realize that all this math is just going to be essentially flipped in the y-axis for the game. So 2D positions. Here's an example. Position A, point A. That's going to be at 4, 2 in the X and Y direction over here. And we can represent that value as a vector, right? So vec2, which we're going to be using, we talked about that a little bit last time. That has an X and a Y. And the vector A represents essentially the distance from the origin, right? So a point at 4, 2, if we draw a vector from 0, 0, the origin, to that point, that's the vector that we have there. Let's say that we have another point at 6, 7. Let's draw that vector as well. And let's do some vector math, okay? So let's take B minus A. What do we get? We get C. And so what we do in order to subtract 2 vectors is just do element by element subtraction. So we take B, X value, which was 6. We subtract 4, we get 2. We'll take B's Y value, which was 7. we subtract a's y value, which was 2, and we get 5. And what we're left with is this c. And what this c actually represents is the vector that goes from a to b, right? So that's actually something like, yes, you could all do that vector subtraction, but it's nice to be able to see, okay, if I actually put that over there at A, it points to B, and that's a useful property, right, that we're going to use. So vector subtraction, if we take destination minus origin, so here, for example, if our destination is B, we take B minus A, that is the distance in both x and y from A to B. And vector addition, origin plus distance equals destination. So origin A plus C, which is this sort of distance vector, will get us back to B. So those are useful things that we can use in here. I'm not going to remind you of SOHCAHTOA. You've all heard this in different schools over the years. But I just wanted to have this one graph here that just, I just want it in the notes, so you don't need to open a new tab. You can just look at it here. So this is just a reference slide. You are all still aware, hopefully, of the unit circle and where all these properties are derived from. And so this unit circle, opposite is y, adjacent is x, hypotenuse is the radius here in the unit circle. If you forgot completely what the unit circle is and all your trigonometry, please just go do some refresher on that. So sine of this theta, that is y over r, which in this case in the unit circle is just y. Cosine of theta is x over r, since the unit circle has a radius of 1, that's just x. Tan of theta is y over x. Okay, just 2 reference slides for you, so you have them there, you don't have to go look them up. Now let's look at an actual tangible example that we're going to be doing in assignment 2. And that is, okay, I have been given angle and distance, and I want to get the vector from that. So I've been given the angle, and I've been given the distance, which here is the hypotenuse. What I want is this x and this y. Okay, so let's see how we would do that. So here's an example of why this is useful, and it has to do with the speed of a traveling object, right? If I give you the speed of something, if I give you the travel of a bullet, let's say I give you the speed, which is how many pixels per frame it should be traveling, and I give you the angle, so let's say I tell you, okay, you're going to shoot a bullet at 30 degrees from the player, and it should be traveling at a speed of 8 pixels per frame. What you have to do in order to update the position of that bullet is figure out the x change and the y change, and then add that to the position of the bullet, right? I can't say, hey, SFML, move this by a speed of 5 at an angle of 30. That function doesn't exist, and even if it did, we want to do this math on our own. So the entity speed is going to be s units per frame. It's going to be traveling at an angle of theta. The radius of the unit circle here is going to be this s, right? If we want to translate this back into the unit circle problem. So cosine of theta is x over r, sine theta is y over r. So if we take the cosine of this angle, that would mean the x change if the speed was 1, right? Because the cosine in the unit circle is the speed if it was 1, or sorry, the x change if it was 1, and sine is going to be the y change if the speed was 1. So therefore, what we've done is we've figured out the x change and the y change if the speed was 1. So to get the actual change, the full x and y change, we multiply it by s, right? So we have our vec2 velocity. So the velocity is the x and y change. The speed is the magnitude of velocity, or the length of the velocity vector. So the velocity from a speed and an angle is just s times cosine s, that's the x change, and s times sine theta, that's the y change. Pretty simple stuff. And again, speed is the magnitude of that. Now let's say we have the opposite problem, right? I've given you the vector of x and y change, and what I want you to find is the distance, or the speed, so the length of the hypotenuse, and the angle. Okay, so how would you do that? Well, if I've given you this player at an x1, y1 position and another entity at an x2, y2 position, then what is the distance from the player to the entity? Well, hopefully, given 2 points, you should all be able to calculate the distance. That's just Pythagoras, right? So the distance, d, again, destination minus origin. So we have the entity x2 minus x1, y2 minus y1. That is this difference vector, d. So that's the vector of the x and y change. And now what we do is we just apply the Pythagorean theorem to get the distance. So it's the square root of the x's squared plus the y's squared. That's it. And make sure you're using square root f. That is just the floating point square root function. What about the angle? Well, I know this difference vector, so I know the y change and I know the x change. Tan theta is y over x, which is d dot y over d dot x. And the way we find out the angle, at least in C++, is this a tan 2f function. So a tan 2f, and be careful because this takes the y value first and the x value second, okay? Don't use, there's an a tan function. I don't know exactly what it does. I just know that you use a tan 2f. All right, so that's how we would solve the opposite problem. The next problem is vector normalization. So the vector's length is the distance that it travels. So again, if we have a vector at 4, 2, that's 4 difference in the x, 4 difference in the y from the origin. And the length L of that vector, again, is just Pythagoras. So x squared plus y squared, take the square root of that. What normalizing a vector does is it maintains the angle. So it's still pointing in the same direction, but it changes its length to 1. So it changes it into a unit vector. And so the normal vector, if we want to normalize a vector, we take our vec2, we take the x and divide it by L, and we take the y and we divide it by L. So we just calculate the length of the vector and divide each of the components by L. Where is that useful? Let's have another example. If we want to shoot a bullet in the game, and assignment 2 has you shooting lots of bullets with a mouse. So we're going to be clicking somewhere on the screen, and that is going to shoot a bullet toward where we clicked at a given speed from a particular location, and that location will be the player. So in assignment 2, the bullet shoots towards where you clicked the mouse. We are given a scalar speed s. So I want the bullet to be traveling at 8 pixels per frame, or whatever I tell you. How do I get this speed vector, or I guess the velocity vector, not the speed vector, that I actually want to shoot it at? So first, what I'm going to do is I'm going to take the distance from where I clicked the mouse and subtract that, or subtract the player's position from where I clicked the mouse. So I get the mouse x minus the player x, mouse y minus the player y. What that gives me is this difference d. Now, you might say, okay, just update it by d. But that's not what we want to do. We don't want the bullet to instantly teleport to where we clicked the mouse. The bullet should travel at the speed specified. So now what we have to do is we have to take this d and scale it so that the speed is what we want. So d has some length L, but we want it to be s, right? So we want to take that same vector, keep the angle, but change the magnitude. So we're going to normalize it first. So we take its length and divide x and y by the length to normalize it. It now has length 1, but we want that to be s, so we just multiply it by s. So we take the normal vector and we multiply each of its variables by s. And so now what we have is a vector pointing in the direction of where we clicked the mouse with the correct velocity to update on each frame. And we could do the same thing if instead of given px and py, instead maybe I gave you the speed and I gave you the angle. Okay, so if I did that, here's the formula instead. So that's just the opposite way of doing the same calculation. Any questions about that so far? Okay. One other thing that we have to do in assignment 2 is circle collisions. And so assignment 2, I'll show, all of next lecture will be about, will be assignment 2, so I'm not going to show it right now. But all of our entities are given circular collision components. So everything is going to be a circle, just to make it nice and tidy. Therefore, each entity will have 2 components that are going to determine whether or not there is a collision between 2 entities. That is the position and the radius, right? So given the position of 2 circles and the radius of 2 circles, we can determine whether or not they overlap. And if they overlap, then there's a collision. So how do we determine this collision? I'm sure you could all figure this out. But essentially, if we draw our 2 circles, right? If visually they overlap, then there's a collision. But we're not using machine learning to see if they visually overlap. We've got to calculate this, right? So essentially, if the distance between the 2 circles, their midpoints, is less than the sum of the radii, then there's a collision, right? That's pretty easy. Over here, radius 1 plus radius 2 is less than the distance between x1, y1, and x2, y2. So there is no collision. Over here, the sum of the radii is bigger than that distance. And so there's a collision. So let's just have a look at that math. Given 2 circles specified by x1, y1, and r1, and x2, y2, and r2, calculate the distance between them. So this is, again, just Pythagoras, right? We've already looked at that. So the distance is the square root of the sum of the squares. And then there's a collision if the distance is less than r1 plus r2. That's it. But who can tell me, even though this is correct, what is not desirable about this? Yep.
I was going to ask this question, that if there's a circle in the left and it has so big of a velocity that it goes to the right at the next frame, to the right of the target circle, without touching that circle, will it work?
So that is a problem that we're going to discuss in a future lecture. But what we will do, so the question was, what if something's going so fast that on one frame, it's on one side of it, and on the next frame, it's on the other side of it, right? The answer to that is, it won't detect the collision. And this is how every wall clip in every video game is done. You get something moving faster than the width of the wall, and then you're on the other side of it. So if those games don't deal with it, we're certainly not going to be dealing with it. There is a physical way to do that simulation in which you can predict when a collision would occur. We're not doing that. The solution to that ends up being do multiple physics updates per render frame so that the distance is so small that will never happen. So typically what you'll do is you'll choose velocities that are less than the width of objects so that we can't have that happen. But I'll talk about that. We've got like 20 minutes of a future lecture on that exact problem with examples from video games. But what I was getting at here was that even though this is correct, we want it to be faster. Why do we want it to be faster? Because square roots are slow. They've gotten a bit faster on modern hardware, but can we do this without the square root? And the answer is yes. Square root is expensive. That's needed if we want the actual distance, right? So if we want to know, okay, from me to you is exactly 3 meters, that's when we need square root. But do we need actual distance here? Well, you might think yes, but look at this. This is the formula. If the square root of this is less than r1 plus r2, what if I square both sides? The inequality still holds, right? And if I square both sides, I get this. So distance squared is just this value squared, right? So it would just be, you just remove the square root. And so distance squared is equal to this. So there's a collision if the distance squared is less than this value squared. And that's pretty easy to calculate. Multiplications are super easy. Additions, super easy. Way easier than square root. And so if I square both sides here, the inequality holds, and I can do the collision check without needing a square root. And so wherever possible, try and get rid of these expensive functions in code that you're going to be calling thousands and thousands of times per frame, right? So this is one of the ways of doing that. So don't calculate the actual distance, because what we're interested in really is just the inequality, right? Now, if there was something where we needed to know the exact overlapping distance, maybe for some advanced physics calculation, sure, then we would need to calculate the actual distance. But for this assignment, we don't need to do it. And I believe the last thing that I'm going to talk about that is needed for assignment 2 is you're going to be spawning enemies in random parts of the window. And in order to do that, you're going to need to generate some random numbers in C++. And the simplest way to generate numbers in C++ is to use the function from C, which is this rand function. Now, for serious security, never use the rand function. Flaws in rand have been pointed out for the last 30 years, but it's fine. We're not doing banking encryption here. We're generating like where enemies spawn in a game, right? So it's fine for this course. There are other classes in C++. You know, you can generate, like you can set up random number generators with specific distributions that have specific cryptographic properties. I don't want this to be like a half-hour lecture on random numbers. Rand is fine for this course. But something to take note is that these random number generators, so when you call rand, it will give you an integer value between 0 and max int, right? So that's what it will give you. But if you run your program 2 times in a row, it will give you the exact same numbers. Why? Because this random function, this rand function, as well as every other random number generator that exists, because in computers it's not true randomness, it's pseudo-randomness, it's just a function creating new unpredictable values, it takes in a seed. And this seed number determines the randomness that you will get for the rest of your program. By default, the random seed for any C or C++ program is just 0. That means if you call rand 1,000 times in 2 runnings of the program with no other factors going into your RNG, then it's going to create the exact same sequence of 1,000 things. That may be desirable, it may not be desirable, but what you can do is seed your own random number with srand. So srand will seed the randomness with a given integer. So the default is 0. If not specified, your program will generate the same sequence every single time, and that may not be fun for the players of the game that we're going to be making for assignment 2, because it means the exact same enemies will spawn in the exact same place with the exact same properties every single time. So the cute hack that people do is they will say, call the time function with null, and what time null will return is the number of seconds that have passed since 1970. That's the C time, right? And so this will give you what is essentially a different integer every time you start your program that you can seed your randomness with. Now, keep in mind that it will, if you do run your program twice in the same second, it will be seeded with the same number, right? But that's very unlikely to happen, that you're running the program, shutting it down, and then launching it again in the exact same second. So I understand that this is horrendously bad practice if you want to generate secure, not actually random, but secure, there's a bunch of properties of randomness, like this is not guaranteed to be super uniform, it is not guaranteed to be cryptographically safe, but it's fine. I just want you to generate some random numbers for a video game. It'll be fine. But what will we have to do is generate random numbers, not only a random number, but a random number within a given range, right? Between some min and max value. And the reason that is because I want you to generate a random position for an enemy that's going to spawn in the game. And so what it has to do is spawn between the left and the right of the screen, and between the top and the bottom of the screen, right? So you're going to have to generate a random number that falls within those bounds. So here's how we do that. if I have given you a min and a max, I'm first going to calculate this difference value. That difference value is going to be 1 plus max minus min. And that is the number of different values that exist in this range, right? And I'll show an example of that in a bit. And then I'm going to say that's my random number that I want, is rand mod diff. Okay, so mod is the remainder from integer division. So is now a random value between 0 and diff minus 1 inclusive. Then I take and I add min to it. And what that will do is add the minimum back to it to get in the proper range. And so this is the full function to generate a random number between a given min and max inclusive. It's min plus rand mod 1 plus max minus min. Let's just look at an example to really drive that home. Let's say I give you a range between 30 and 40 inclusive. Well, there are actually 11 different values there, right? 30, 31, 32, 33, 34, all the way up to 40. That's 11 different values. That's why we have this 1. Is equal to rand mod 11. This will give me a number between 0 and 10 inclusive, but I wanted between 30 and 40 inclusive. So if I add 30, I'll get 30 plus a random number between 0 and 10, which is the same thing, the thing that I wanted in the first place. And this even works if I have a range which is the same. So between 20 and 20, rand mod 1 plus 20 minus 20, that is always going to give us 0. And so 20 plus 0 will be this. Will just be 20, right? So it'll work as long as you give it a min that's lower than a max.